Good afternoon, students.
Good afternoon, sir.
Only less number of students are there. I am seeing only 22 have joined. You had a class before that, 11 to 12. Class was there.
Yes, sir.
And how many students were there in the class?
2025.
Why so less?
19.
Why so less number of students?
It might possible because of exam.
Good. So you had a class from 10 to 11 and 11 to 12.
Yes, sir.
And in both the classes, student strength was like this only.
Yes, sir.
So today I'll take up basics on MOSFET. That is how the MOSFET works. It would be just a revision of what you already know about the MOSFET circuit, right? But as we are primarily dealing with a MOSFET device, it is necessary to revise that basics of MOSFET, how it works, right? And what are the second order effects, and how you can model a MOSFET and use that model in analyzing the MOSFET based circuits. Is the slide visible to everyone?
Yes, sir.
Right. So this is a basic 3D-dimensional view of a MOSFET. It is known as metal oxide semiconductor field effect transistor, right? It has four terminals: gate, drain, source, and body terminal, right? Why it has become so popular? You'll see that as the technology has progressed, that it has become easy to fabricate MOSFET. It has an overall better performance as compared to BJT. It is cost effective, economic. You can reduce it to a very small size. The best advantage of MOS circuit is that you can scale it to a very low dimensions. And there is a continuous performance enhancement. So what you are seeing in the figure is a P-type, N-type MOSFET. If you have an N-type MOSFET, you will have a P-type substrate, right? And in this P-type substrate, you will have two doped regions. One is the source region, another is the drain region. These are N-type doped. They would be separated out with a gate region. And in the gate region, you have a P-type substrate. Then you have a silicon dioxide insulating layer. And on the top of silicon dioxide, you have a metal layer. So that is why it is known as metal oxide. Metal is your this gate region, oxide is your that is insulating layer between the metal and semiconductor, and metal oxide semiconductor field effect transistor. Nowadays you don't use this metal, use a polysilicon, use a highly doped polysilicon, as it has a better adhesive property with silicon dioxide, but the name still goes on: metal oxide semiconductor field effect transistor. This is the source region. To have a contact, you have a metal on this source region. Similarly, you have an N-type drain region, you have a metal contact on it. And in P-type MOSFETs, you have the N-type substrate and heavily doped 2P regions. So this is the top of the gate, right? It is a heavily doped polysilicon gate. Conductivity can be increased by depositing metal or metal silicide over the gate. Basically, it is a heavily doped polysilicon. Further, you can increase the conductivity by depositing metal or metal silicide over the gate region. P-type substrate, it is a single crystal silicon wafer that provides physical support for the device. Then you have a heavily doped N regions for source and drain. This is source and drain. Thin layer of Si that insulates gate and substrate. And this dimension between the source and drain is known as the channel length, right? And from here to here, that is this end to this end, this is known as the width of the channel. And you'll see that the current that flows from the drain to source region is dependent upon this aspect ratio, W by L. That is the width of the channel and the length of the channel. And further, what we are seeing here is that though the gate region extends from this to this, and your intended channel length was from this end to this end, but when you are fabricating a MOS transistor, what happens? You have a P-type substrate, and then you want to convert this into N-type, and again this into N-type. You either do a diffusion or you do an ion implantation, right? So you're depositing impurity in P-type substrate to make this N region. You want to make it this N region. But because of the diffusion, they will diffuse sideways. So you get an overlapping region between the gate and source, overlapping region between the gate and drain. So your actual length gets reduced, right? This is what you'll see. Nmos FEB, if you had a length varying from 1.1 to 3 micron, width varies from 0.2 to 100 micron. Now the device dimensions have come down. You have a channel length varying from, say, 5 nanometer itself. Smallest channel length is 5 nanometer, 7 nanometer. So previously you used to have 0.1 to 3 micron, but because of the scaling, this channel length has gone down. And your gate oxide thickness also previously, which was from 2 to 50 nanometer, has gone down to the range of 1 nanometer. L, what you're seeing is the effective length of the channel. Takes into account the diffusion that occurs in the implantation of source and drain region. This diffusion you can't avoid. There is going to be certain amount of diffusion below the gate region. So your effective channel length goes down. Silicon dioxide, which is between the gate and the substrate region, is essentially a glass. Glass is very good insulator. Thus, no current can flow from gate into the MOSFET device. And this silicon dioxide layer is sandwiched between the metal gate or say a polysilicon, heavily doped polysilicon gate electrode and a P-type substrate. So initially this used to be metal. That is, this was a metal initially. So that is why you have the name. These three materials that give the MOSFET its names is metal, that is a gate electrode, oxide, insulating layer, semiconductor, that is substrate. And we'll see that this transistor is symmetric. Drain, which is equivalent to BJT's collector, and the source, which is equivalent to BJT's emitter, are fully symmetric and therefore interchangeable. In MOSFET, the terminal, in N-type MOSFET, the terminal which is connected to the highest positive potential act as a drain, and which is connected to lower potential is act as a source. And they are interchangeable. Whereas in the case of BJT, you can't interchange collector and emitter terminal, right? Whereas in the MOSFET, these are interchangeable depending upon the potential to which that terminal is connected. It behaves as, if it is a positive potential, it is behave as a drain. Unlike a BJT transistor in which one of the PN junction is typically forward bias and the other reverse bias, in MOSFET, all the PN junction must be kept reversely biased. This we ensure because we don't want a connection between the drain and substrate. And similarly, we don't want a connection between the source and substrate region. So what we'll do, we'll keep the source and substrate region reverse bias. We'll keep the drain and substrate region reverse bias. And this we do by keeping the substrate at the lowest potential. Your substrate is P-type, you keep it at a lowest potential. You'll see that the junction formed between the substrate and N-type source or N-type drain is reverse bias, because we don't want any connection between the source and substrate and drain and substrate. We want a connection between the source and drain. So what we do is that body or the substrate terminal is typically connected to the most negative DC voltage in the circuit in case of P-type substrate, or to the most positive DC voltage in case of N-type substrate. Very often we simply short circuit the body terminal to source terminal. These are the typical symbols for N-type MOS circuit, right? The current coming out of the source terminal, right? You have a substrate terminal also indicated. Sometimes you don't have a substrate terminal, but that this current is coming out of the substrate source terminal. That means it is an N-type MOS. If the current is going into the source terminal, it is a P-type MOSFET. Sometimes you have a 4-terminal shown on the symbol. Sometimes you don't. If the source, that is the substrate terminal, is not shown, that means that substrate is connected to the most negative supply or to the ground in the case of Nmos transistor, and in the case of Pmos, it is connected to the most positive supply. Now, if you see this MOS, at first glance, no current can flow from drain to source, right? Because here you have a PN junction between the source and substrate. You have a PN junction between, and we have reverse bias this. So current cannot flow into the channel from the drain, as this requires current flowing from the N-type region into P-type region. Similarly, current cannot flow into the channel from source, as this requires current flowing from the N-type region into P-type region. And further, current cannot flow into or out of the channel from the gate, as Si2 layer is a very good insulator. So it would be really useless if no current can flow from drain to source. However, we can modify the channel so that this current can indeed flow. So what we need a channel between the source and drain region. So what we do, we must induce a channel, that is, create a thin layer of N-type channel connecting source and drain. Then only this is useful. So how do you induce a channel? For inducing a channel, we place a positive voltage at the gate electrode. This positive voltage at the gate electrode creates an electric field within the P-type substrate, which pushes the positively charged holes into P-type substrate away from the gate region. A depletion region is formed in the silicon under the gate. So what has happened, because you have added a positive voltage to this gate terminal, now this positive potential, there are holes here in the P-type substrate, it pushes away those. If you push it away, you will have a depletion region in the silicon under the gate region. So there was a depletion region between the source and substrate because this was N and this. There was a depletion region between drain and substrate because the PN junction is here. And at the PN junction, you have a depletion region. But then you also have a depletion layer between the gate region and the substrate, because the positive potential of the gate has pushed down the holes from this region to deep down. The electric field under the gate will repel positively charged holes, right? But will attract negative charged free electrons. The minority carriers in the P-type substrate, that is, the free electrons, are attracted towards the gate electrode because of the positive potential. And we'll see that many of the electrons that are attracted also comes from the heavily doped source region and heavily doped drain region. So how a channel is created for the current flow? There is a silicon dioxide insulator separating the gate electrode and the silicon substrate. So the free electrons are attracted by gates simply pile up at the top of the silicon substrate just under the SiO2 layer. Now when electrons are piled up in the gate region, what happens? It results in an inversion layer, a thin layer in the P-type silicon where the majority carriers are actually free electrons. And this inversion layer forms an N-type conducting channel connecting the N-type drain to N-type source. And this has been done by applying a positive voltage to gate. We have induced a conducting channel. In other words, the current flowing from drain to source no longer encounters any PN junction. So if you have given a positive voltage, what has happened? The substrate region below the gate region has been inverted. Previously it was P-type, now it has become N-type. So will any positive gate voltage suffice for inducing a channel, or must this gate voltage be somehow sufficiently large? The answer is that yes, the gate voltage must be sufficiently large to create an inversion layer. It must be sufficiently large to induce a conducting channel. So in fact, the voltage value must exceed some threshold value Vt. Then only the channel is formed. So your gate to source voltage has to be greater than the threshold voltage of a certain MOS device. Then only a channel is formed between the drain and source region. And we see it that the region below the gate has been inverted from P type to N type. So when your gate to source voltage is less than threshold voltage, no channel is formed, and this channel, no current flows between the drain and source voltage. If your gate to source voltage is greater than threshold voltage, channel will be formed and a current is going to flow. And this threshold voltage typical value is from, say, from 0.3 to 0.5 volt. So if your gate to source voltage is less than this threshold voltage, no channel formed, no connection between drain and source, and transistor is said to be in cutoff mode. Now, if your gate to source voltage is greater than the threshold voltage, a channel is formed, but still there is no current because there is no potential difference between drain and source terminal. Your VDS is zero. And we'll see that as you keep on increasing gate to source voltage, what is going to happen? The more electrons are going to get attracted in the channel region, right? Your conductivity of the channel is going to increase and its resistance value is going to reduce. The process of increasing the induced channel conductivity by increasing the gate voltage is known as channel enhancement. And that is why we have the term enhancement MOSFET. Right? One is depletion MOSFET, another is enhancement MOSFET. So this enhancement MOSFET is when your conductivity increases with the increase in gate to source voltage. Now there is a third case when your gate to source voltage is greater than the threshold voltage, but your drain to source voltage is less than VGS minus VT. What we say is the transistor operates in the triode mode or linear mode. A current proportional to VDS starts to flow from drain to source. The transistor in this state behaves as a voltage controlled resistance. We assume that VGS minus VT is constant and VDS is being varied. So in fact, there was two PN junctions in Nmos device which were reverse bias. So there was no chance of current flowing. But we have seen that as you apply gate to source voltage greater than the threshold voltage, a channel gets induced between source and drain region. The P region, that region which was P type, gets inverted into N type, and then there is a conduction from drain to source. And we say that because of a side O2 layer at the gate region, the gate current is zero. Thus, all the current entering the drain will exist from the source. And we conclude that drain current is equivalent to source current. And as a result, channel current for the Nmos device is simply referred as a drain current. For small VDS, the drain current will be directly proportional to VDS. We say that the transistor conducts in the triode region and behaves as a resistance. If VDS is zero, the drain current is zero. If VDS increases by 10%, drain current will likewise increase by 10%. For small values of VDS, the channel resistance is defined as VDS by ID. Only the condition here is that the gate to source voltage should be greater than the threshold voltage, and VDS has to be smaller than VGS minus VT. So the value of the resistance depends upon the conductivity of the induced channel, which in turn is dependent upon VGS minus VT. So in other words, the channel behaves like a voltage controlled resistor. So if you increase VGS minus VT, what is going to happen? The conductivity is going to increase, the resistance is going to go down. So for the same drain to source voltage, you are going to have more current, right? So as VGS minus VT increases, the drain current increases for same drain to source voltage. And we see that the resistance of the MOS is dependent upon VGS minus VT. So this RDS has a meaning only when VDS is small. And most often we'll see that this VDS is not small. This VDS is greater than VGS minus VT, right? So this transistor, which behaves as an resistance, is only for a smaller value of VDS. So now what is going to happen? Initially, when this VDS was small, your gate to source voltage was able to increase the electrons and was able to change the conductivity. Now, after sufficient, that is when your drain to source voltage becomes greater, it attracts electron of its own, right? And as a result, what we'll see is that current starts saturating. And what we'll see is that as you keep on increasing drain to source voltage, the conductivity of the channel gets reduced here. This is because positive current entering the drain will actually consist mainly of the free electron exiting the drain. As a result, the concentration of free electrons in the inversion layer began to decrease in the vicinity of the drain. In other words, increasing VDS will result in decreasing channel conductivity. Because your VDS has increased, it pulls the electron towards this region. The concentration of the electrons near to the drain region decreases as compared to the concentration of electron near the source region. And with further increase, we'll see that the channel just reaches the drain. The channel is reduced to zero inversion charge at the drain. And we say that the channel gets pinched off at the drain region. However, the drifting of electron is not going to stop, the drifting of electrons through the depletion region between the channel and drain becomes. And this stage is known as the pinch off. So at the pinch off, there is no more increase in the drain current as VDS increases. So what we have seen is that when your VDS is smaller than VGS minus VT, concentration of the electrons in the channel range is determined by gate voltage. And it is uniform across the channel. Whatever is the concentration of electron at source, same is the concentration of electrons at the drain region. If your VDS is smaller than VGS minus, you have an uniform channel region between source and drain region. Now, as you keep increasing VDS, and if this VDS goes beyond VGS minus, what is going to happen? The electrons near the drain region are going to get pulled up by this drain voltage. Concentration of the electron decreases here, and the conductivity here decreases. And at a point when your VDS is much greater than VGS minus VT, pinch off take place, right? And the electrons don't stop. The number of electrons that cross from the gate region, that is channel region to drain region, becomes constant. They start differing from the depletion region into drain region. However, the number of the electrons flowing from the channel to drain region becomes constant. They do not increase, and we say that the current has saturated. And as the current, we say that there is no more increase in the drain current as you increase drain to source voltage. So if we continue to increase VDS after the channel is pinched off, does the drain current actually begin to decrease? No. And an interesting thing happens when the channel is in pinch off. As we further increase VDS, the drain current will remain unchanged approximately. That is, the drain current will be constant with respect to VDS. It is not going to increase, but it becomes constant. That is for the ideal MOS transistor. So when your VDS is less than VGS minus VT, it behaves as an resistance. You have a linear relationship between ID and VDS, right? It is only when VDS start increasing and becomes nearer to VGS minus VT, we'll see that your channel width near the drain region start decreasing and its conductivity starts reducing. And we'll see that as the conductivity reduces, the channel resistance increases. And beyond pinch off, the current becomes constant. So if your drain to source voltage is greater than gate to source voltage minus threshold voltage, the channel is pinched off and the drain current becomes constant. And what we see is that in this region, the MOS transistor behaves as a current source. That is, we see that what is the property of the current source? Property of the good current source is that its resistance is infinite. So if you see that the slope is zero, that means that this is a curve between ID and VDS. So the slope is zero, that means the resistance is infinite. So whatever is the voltage across this device, the constant current flows through it. Right? So this behaves as an ideal current source beyond the pinch off. So to summarize, when your VGS minus VT is less than zero, no channel is induced, no inversion line is created, so drain current is zero. We call that MOS transistor is in cutoff. Only when VGS minus VT is greater than 0. That means the gate to source voltage is greater than the threshold voltage, and an induced channel is present. But the value of VDS is not enough to pinch off this channel, and Nmos is said to be in triode mode, and the current in the triode mode is going to increase with the increase in VDS voltage. And when your VGS minus VT becomes, your VDS becomes greater than VGS minus VT, what we say is that the channel gets pinched off and the current becomes constant, and it no longer increases with the increase in drain to source voltage. And we say that the MOS transistor is in saturation region. So similar to Nmos, we can have a Pmos transistor also, right? The structure of Pmos device is essentially same as Nmos transistor, except that wherever there was N-type silicon, there is now P-type silicon, and wherever there was P-type silicon, there is now an N-type silicon. Especially the Pmos channel is a part of N-type substrate lying between two heavily doped P wells beneath the source and drain electrode. And we'll see that this is only Pmos is constructed in consort with a Nmos transistor. That is, mainly we'll be using the Nmos transistors, but we'll be having a Pmos transistor also, and they will be constructed in consort with the Nmos. And the pair of Nmos and Pmos transistor is known as complementary MOSFETs, CMOS for the short. So where you use both the Pmos and Nmos, both are used, we call it as a CMOS. So you have a P-type substrate. On this P-type substrate, you have an N-type source, N-type drain, right? Then you have a thick silicon oxide layer by isolation. And you want to have a Pmos transistor, what you will do, you will fabricate an N-type well on the P-type substrate, right? And in this N well, this N-type acts as a substrate for Pmos. In this, you will have a P-type drain, P-type source. Right? To create an inversion layer in N-type substrate, we must attract holes to the gate. As a result, the P-type channel will be induced, connecting the P-type drain and source. However, to attract holes towards the gate, the voltage VGS must be sufficiently negative. So for Pmos, the threshold voltage is negative value, so that the channel is induced only if VGS is less than threshold voltage. That is, VGS is more negative than VT. A channel is induced in Pmos device, right? Only if VGS minus VT is less than 0. Similarly, we typically get current to flow through the channel by making a voltage VDS negative. If we make the voltage VDS sufficiently negative, the P-type induced channel will pinch off. So when VDS is negative, the drain current will flow from Pmos source to Pmos drain. This is exactly opposite of the Nmos device with the positive VDS. So what we do in the Pmos device, we connect the source to the most positive supply. So you have a drain to source voltage which is negative. Then only the current flows. This is, you have it on this curve on the second quadrant. Current flows only when VDS is negative. So the curves are similar to that of Nmos type. only the polarity of the drain to source voltage is reversed, gate to source voltage is reversed. So when VDS is less than VGS minus VT, saturation takes place. If VDS is greater than VGS minus VT, the transistor is in triode mode or in the linear mode. So IV characteristics of an Nmos transistor, we assume that substrate is connected to the ground, that is, source is connected to the ground, substrate is also connected to the ground, so VSB value is 0. If VSB is 0, VT is constant along the channel, right? If source and the body terminal are connected to the ground, VT is constant along the channel. EX dominates, EY need to consider current flowing only in the X direction. EX dominates EY and need to consider current flow only in the X direction. This is the assumption that we make. So when VGS is less than threshold voltage, it is in cutoff and no drain to current source is going to flow. So when VGS is less than VT, cutoff MOSFET is in cutoff, drain current is simply 0. Linear mode when VGS is greater than VT, but your VDS is less than VGS minus VT. The channel is going to reach the drain region. So let VECX be the channel voltage with respect to source at position X. You'll see that the voltage, because drain voltage is connected to a high positive voltage, source is connected to 0. As you move from source to drain, the VDS voltage is going to increase. And let VCX be the channel voltage with respect to source at position X. Boundary conditions are that this control voltage at X is equal to 0 is good, be equal to the source voltage, which is equal to 0. And when this X is equivalent to channel length, its voltage is the drain voltage, which is connected here. The charge density along the direction of the current is given by W is the width of the channel, COX is the gate oxide per unit. This is per unit area. COX is the gate oxide capacitance per unit area, VGS minus VT. So W is the width of the channel. So WCOX is because COX is the gate oxide capacitance per unit area, WCOX is the capacitance per unit length. And we'll see that in this channel, the potential varies from 0 at source to VDS at the drain. So your charge density in the channel region is nothing but WCOX, VGS minus VCX minus VT, where VCX is the channel potential at X. So if you want to find out the current in the channel region, you multiply the charge density by its drift velocity, where V is the velocity of charge in meter per second. So current is nothing but charge density multiplied by the drift velocity, right? And we see that the drift velocity is nothing but the mobility multiplied by electric field. Mu n is the mobility of charge carrier. E is the electric field in the channel given by gradient of the potential. That is minus dV by dx. So we replace drift velocity here by expression mobility multiplied by electric field. Electric field expression is nothing but the gradient of voltage. So expression for the drain current becomes nothing but WCOX VGS minus VC x minus Pt multiplied by mobility into dV by dx. Now applying the boundary condition for Vx, you integrate the equations from x is equal to L. So x is equal to 0, we see that the voltage is 0, which is the source voltage. At x is equal to L, the voltage is drain to source voltage. Replace the expression for ID, which is mu WC aux VGX minus Vx minus Vt. Mu and dV by dx cancels out. Here you have dV. Now if you integrate it, you're going to have this. That is, this will be ID into L. This will be half WC aux. You have to integrate it. VGS minus Vt will get multiplied by V. So if you integrate it and apply the boundary condition, this is what value you get. Half mu and C aux W by L bracket 2 VGS minus Vt, VDS minus VDS whole square. And if you take the 2 outside, and we'll see that this is going to be maximum when VDS is equivalent to VGS minus Vt. It will have the maximum value when this VDS is equivalent to VGS minus Vt, and that value is given by half mu and C aux W by L. It is going to be VGS minus Vt whole square. So we'll see that the drain current is dependent on the constant of technology, that is mu and C aux, device dimensions W and L, and the gate and drain potential with respect to source. So this is the expression for the drain current in the triode region. And when your VDS is equivalent to VGS minus Vt, that it gets pinched off and it has a maximum current. And this is the expression for the current in the beyond the pinch off region or in the saturation. So in the linear region, you have this current. In the saturation region, you have this current. And the current is independent of drain to source voltage. So in linear region, when the drain to source voltage is 2 less than VGS minus Vt, you can approximate the drain current by this expression. Mu and C aux W by L, VGS minus Vt, VDS. That is, in the deep triode region, it behaves as a resistance. So the triode region expression is this. Only when VDS is very much less, we say that it is in the deep triode region, expression becomes this one. Half mu and C aux W by L, VGS minus. And we'll see the resistance exhibited is equivalent to 1 upon mu and C aux W by L. Only when your drain to source voltage is much less than 2 VGS minus VTH. This is within this circle. And if you expand this circle, magnify it, you'll see that this behaves as a resistance. And the value of the resistance is dependent upon the value of gate to source voltage. So in this region, the transistor behaves as a resistance, and the value of the resistance is given by this expression. If you change the value of VGS, the resistance is going to change. So gate controlled resistance you have between source and drain region. This is in the deep triode region when your VDS is much less than 2 VGS minus VTH. For small value of VDS, the drain current can be thought of straight line, implying that the path between source and drain can be represented by a linear resistance, right? So the MOSFET transistor operates as an resistor whose value is controlled by overdrive voltage. This is known as the overdrive voltage, VGS minus VT. So this is expression in the drain current. When your drain to source voltage is equivalent to VGS, we say that this gets pinched off and the drain current becomes constant. Mu and C ox by 2 W by L VGS. So this is the saturation region. This is for the ideal MOSFET where you don't have a second order effect, right? And when you try to use a transistor, you try to bias it in the saturation region, right? When you want to use a MOSFET as an amplifier, you will bias the transistor in saturation region, and it is in this region where the transistor is going to be. And in this region, we'll see that the current that flows into transistor is independent of VDS. It depends upon what is the gate source voltage, right? So in saturation mode, the drain source current is almost constant, and the value of the constant current depends upon VGS. So the MOSFET transistor therefore acts as a voltage-controlled current source. So what we see here is you are modeling a transistor by current source, and we see that this current is dependent upon the gate to source voltage. Value of this current is nothing but half, that is mu and C ox W by L VGS minus VT whole square, right? And the value of the voltage VGS is between the gate and source. This is the gate terminal, this is the source terminal, and this is the drain terminal. And you have a current between drain and source terminal. The value of the current is determined by gate to source voltage. This is the case of an ideal MOS transistor. And it is important to mention that above current formulas are exactly same for the case of Pmos transistor, where all we do is to replace the electron mobility by hole mobilities. And we have to keep in mind the inequality signs in triode versus saturation are inverted. So VDS less than VGS minus VT, that is Nmos is in triode region, or Pmos is in saturation mode. If VDS is greater than VGS minus VT, that means Pmos is in the triode mode or Nmos in the saturation. So that's the end of lecture today, right? Yeah, I'll share the slides on the Google Classroom. So our next class will be after your exams.
Yes, sir.
That is on the 21st of Feb, right? So wish you all the best for your 5th semester exams. Do study hard, do well in the exams, and we'll meet after your exams are over, right? So I'll end my lecture here.
Thank you, sir.
Okay, welcome. Wishing all of you best for your exams.
Thank you, sir.